Above a silent Alaskan roadside, the northern sky begins to move, glowing like something alive over fresh snow. From the ground, one observer looks small beneath a curtain of light stretching far beyond the road. The light does not sit still. It ripples across the stars like wind, passing through invisible fabric. Pulling away from Alaska, the glow becomes a thin signal on the edge of the whole planet. What looks local from a highway shoulder is actually part of a system, wrapped around Earth itself. Most of this system is invisible, yet its effects can paint the sky in moving color above us. The familiar night sky is not a ceiling, but the lower edge of space weather touching Earth. High above the atmosphere, Earth's magnetic field bends the incoming stream instead of letting it strike directly. The beauty begins as a disturbance, a quiet clue that energy has traveled from the sun toward Earth. By the time we see color, a much larger journey has already happened overhead far above us. Space around Earth may look empty, but it behaves more like a changing environment than a void. Scientists call this space weather because conditions near Earth can shift, strengthen, and sometimes become disruptive. Unlike rain or wind, this weather begins with charged particles and magnetic fields moving through space. NOAA watches these changes the way meteorologists watch storms, searching for signals before impacts arrive near Earth. A satellite above the planet can sense a disturbance long before anyone sees color in the sky. Each measurement becomes part of a forecast, turning invisible space into something people can track and prepare for. The aurora is only the visible edge of a forecast system stretching between sun and Earth itself. If space weather strengthens, signaling to the upper atmosphere can begin behaving less predictably than expected. That is why the glowing sky matters beyond beauty, especially in a world guided by satellites every day. The same planet that shows the lights also depends on systems passing through disturbed space above it. From orbit, Earth's night side reveals cities, clouds, oceans, and the faint edge of atmosphere glowing softly. That thin atmospheric edge is where invisible energy can become the aurora people recognize from the ground. The question is not only why the sky glows, but what controls when it happens above us. Space weather gives the answer, linking sunlight magnetism, particles, and Earth's protective field into one system. When the sun grows restless, the environment around Earth can change before the surface feels anything. Forecast centers look for patterns, because the first warning may come from instruments, not human eyes. A quiet screen in a control room can reveal the storm behind a beautiful northern horizon. The more scientists watch, the clearer one fact becomes: Earth is not isolated in space at all. It is surrounded by streams, fields, and charged particles that can shift from calm to intense. To understand the lights, we have to follow those particles back toward their source, the sun. The trail does not lead downward into weather, but outward across space toward our nearest star. Long before an aurora forms, the sun has already released matter into interplanetary space around us. That matter is not smoke or fire, but a thin flow of charged particles leaving the sun. Some days the stream is gentle, other days solar activity pushes more energy toward Earth than usual. The aurora becomes easier to understand when the sun is treated as an active, changing place. On monitors and satellites, watch the changing star for patterns moving in our direction toward Earth. A solar disturbance can cross space silently, carrying magnetic conditions that decide how Earth responds later. Not every disturbance becomes dramatic, but the strongest ones can widen the auroral zone farther south. For viewers below, the result may look peaceful, even when the source was powerful and distant. Chapter 1 leaves us with a new question. What exactly is the sun sending toward Earth? The sun does more than shine. It constantly breathes a thin stream of particles outward through space. This solar wind is invisible, but it can shape the magnetic environment around every planet it reaches. Near the sun, magnetic loops rise and twist, storing energy above the bright surface below them. When those fields rearrange, part of the sun's energy can be launched into space around it. Some eruptions are vast, but even the regular solar wind keeps pressing outward from the sun. To human eyes, the sun looks steady. To instruments, it is restless and magnetic every day. Those instruments give Earth advance, measuring speed, density, and direction before particles arrive near orbit. A bright solar loop may look distant, yet its magnetic story can continue across space toward Earth. The aurora begins here, not in the Arctic, but in a star that never truly rests. As the camera leaves the sun, the next question becomes how Earth receives that stream from space. The sun looks steady from Earth, yet its surface churns with restless texture and hidden magnetic force. Each bright grain rises and fades as hot plasma moves beneath what we call a simple sunrise. A single solar feature can dwarf a city block, reminding us that familiar daylight comes from immense machinery. Magnetic fields guide glowing plasma into loops, shaping the sun's atmosphere like invisible hands, pulling fire upward. Spacecraft watch these motions in wavelengths our eyes cannot see, turning hidden solar behavior into evidence. What seems like a calm star is really a restless engine, constantly rearranging energy above its surface. Along one bright arc, charged material slides and twists, following magnetic paths that are still changing. These loops are not decoration. They reveal how the sun stores, releases and redirects enormous magnetic energy. From this activity, a thin stream of charged particles begins moving outward into the solar system. Human eyes cannot see that stream, but instruments can trace its path away from the sun. Solar wind is not a rare blast. It is a constant flow leaving the sun every moment. Inside that flow are charged particles and magnetic structure, traveling outward like weather without clouds or familiar storms. Unlike a breeze on Earth, this stream crosses millions of miles through space before meeting anything solid. Its speed and density change, which means Earth never faces exactly the same space weather twice. Some regions of the sun open wider, letting faster streams escape into interplanetary space for days. When a faster stream catches a slower one, the boundary between them can build stronger pressure. That pressure matters because Earth does not meet a smooth river, but a changing magnetic current. The sun's magnetic field rides with the wind, carrying direction as well as particles through open space. When the field turns the wrong way for Earth, more energy can enter our magnetic environment. A stronger disturbance may leave the sun quietly, then spend days crossing the darkness toward Earth. Sometimes the sun lifts a vast cloud of material above its edge, larger than ordinary solar wind. This kind of eruption can expand through space, but it does not always travel toward Earth. A bright flare is a flash of radiation. A mass ejection is moving solar material through space. The difference matters because Earth responds to what arrives, not simply to what appears dramatic near the sun. Seen from space, an eruption can spread outward like a swelling front through the solar wind. Yet even a large front may miss Earth completely, passing above, below, or beside our orbit. Scientists follow its shape and direction, looking for signs that the disturbance could intersect our planet. The question is not only size, but speed, density, and the magnetic direction carried inside the cloud. A cloud that reaches Earth with the right orientation can disturb the planet's magnetic shield. Until that orientation is known, the glowing sky remains possible, not guaranteed, for observers waiting below. Inside the stream, space weather feels less like empty space and more like a moving magnetic ocean. Particles do not travel alone. They carry fields that bend, twist, and reconnect far from the sun. A spacecraft sampling this flow measures speed, density, and magnetic direction before the disturbance reaches Earth. Those measurements become clues, but even good clues still leave uncertainty in timing and storm strength. Forecast models turn the data into moving maps, showing where the solar wind may go next. For people on the ground, that invisible motion may later appear as color across the sky. The journey from Sun to Earth is long enough for forecasts, but short enough to matter. A disturbance crossing space can change shape, making its arrival less certain than a simple clock. By the time it nears Earth, the stream has become a moving test of our planet's shield. So the next question is simple. What happens when solar wind reaches Earth's invisible boundary? Earth appears calm from orbit, even as charged particles approach from the sun, facing side in steady waves. The first meeting is not a crash into air, but a pressure against magnetic space around Earth. Earth's magnetic field pushes back, forcing much of the flow to bend around the planet. Like water around a rock, the solar wind reshapes itself, while the obstacle also flexes under pressure. On the sunlit side, the shield compresses, proving protection is dynamic rather than solid or fixed. Behind Earth, the same magnetic field stretches into a long tail pointing away from the sun. This tail stores part of the energy, turning Earth's night side into a hidden magnetic reservoir. The shield protects life below, but it also guides energy toward the polar atmosphere above Earth. That guidance explains why auroras prefer high latitudes, where magnetic pathways reach downward more easily into air. Deep in the tail, stored energy waits for the next step, becoming light in the sky. From the dark magnetotail, Earth appears protected, yet something invisible keeps bending under the solar wind around us. This shield is not a wall, it is a moving magnetic region constantly shaped by pressure from space. On the sunward side, the solar wind presses the boundary inward, like river water striking a rock offshore. Earth's magnetic field holds its shape only by constantly adjusting to what the sun sends next each hour. The invisible boundary breathes, tightening on one side while stretching far into space behind Earth's night side into darkness. A satellite crossing this region would measure changes no human eye could ever see directly from the ground. What looks calm from the ground is a moving shield, reacting every moment to solar wind above us. Field lines in this visualization are clues, not glowing wires hanging in space around Earth itself for viewers. Scientists map the shield by watching particles, magnetic changes, and spacecraft readings across near-Earth space, piece by piece. The first surprise is simple. Earth survives the sun because the shield is flexible, not a rigid wall. As pressure rises, the dayside field compresses, and stored energy begins shifting toward the nightside tail behind Earth. That stretched tail can reach far beyond Earth, quietly holding energy from the solar wind stream behind us. The magnetotail is not empty darkness. It is part of Earth's larger magnetic circulation system in space itself. When the tail becomes disturbed, particles can be redirected back toward Earth's upper atmosphere near the poles again. This is where a protective shield begins to behave like a pathway for incoming energy streams from space. The energy does not fall everywhere. Magnetic geometry guides it toward polar regions instead of spreading worldwide evenly. From above, the poles become the places where visible space weather finds a doorway into air and light. This is why auroras often circle the Arctic and Antarctic like glowing crowns around the planet at night. The pattern is called an auroral oval, and it expands when geomagnetic activity grows stronger across polar skies. A stronger storm can push the oval southward, bringing northern lights closer to American cities temporarily after dark. For viewers in Alaska, Minnesota, Michigan, or Maine, the sky can become a forecast map overhead on rare nights. But that map changes because the sun, not the ground, controls the incoming energy from space above Earth. A quiet aurora may look soft, while a stronger event can ripple across the horizon rapidly in waves. The movement is not wind in the air. It is energy reorganizing high above weather systems and clouds. In this hidden region, magnetic tension can snap and reconnect, releasing stored energy toward Earth again at speed. Reconnection sounds violent, but it describes magnetic fields, changing partners, and redirecting particles along new paths through space. That redirected motion helps explain why the aurora can suddenly brighten, twist, or pulse over minutes without warning. The sky's beauty, the visible ending of a process that began in invisible space weather, far away. Each ripple above the poles at a larger magnetic system, still adjusting around Earth, tonight in darkness. The shield protects life below, but it also carries signals from the sun toward our atmosphere every day. From orbit, the auroral oval can appear like a ring of faint fire around polar night below spacecraft. Its shape tells researchers where energy is entering and how the magnetic shield is responding now to pressure. Ground cameras see the glow, while spacecraft measure invisible causes moving above it through orbit in real time. Together, the views turn a beautiful sky into evidence from a planetary scale system surrounding Earth itself in space. The more scientists compare them, the clearer the hidden connection becomes between sun and atmosphere tonight above us. The aurora is not painted on the sky. It's produced inside the upper air itself by collisions. To understand the light, we have to leave the shield and enter the atmosphere above Earth where particles arrive. The next clue is chemical, hidden inside oxygen, nitrogen, altitude, and energy above the polar night waiting for us. A green glow is not just color, it is a message from excited atoms high above the ground. May come from higher air, where collisions become rarer and slower to fade into darkness. Now the invisible shield has delivered energy to a place where gas can answer with light above Earth. The atmosphere is thin here, but it is not silent to incoming particles from space above at all. Each collision can lift an atom into an excited state, storing energy briefly before releasing light outward again. When that energy escapes, the sky reveals what the eye could never track, particle by particle from below. The colors are not random. They depend on gases, altitude, and the energy involved in collisions above us. This is the bridge from space weather to light, from magnetic motion to atmosphere, above Earth at last. The aurora becomes Earth's translation of solar energy into something human eyes can read from below at night. But the translation is incomplete until we understand why different colors appear at different heights overhead above Earth. Green, red, purple, and blue each pawned a different atmospheric story waiting above the poles tonight quietly. The shield has guided the energy. Now the atmosphere will reveal what each color means next in light. The story now enters the upper polar, where invisible particles begin meeting the thin air above Earth. This is far above ordinary clouds, near the edge where familiar weather gives way to space. When a charged particle strikes an atom, it can leave that atom carrying extra energy for a moment. The aurora is not reflected sunlight. It is air releasing energy as its own colored light. Across the polar night, a thin glowing layer stretches quietly above mountains, forests, ice and water. Instruments can see particle streams, and ultraviolet emissions long before the human eye notices the full glow. What looks like light painted on clouds is actually high-altitude gas, responding to energy from space. A viewer in Alaska sees the final glow, while the invisible collision chain happens far overhead. The light forms above airplanes, storms, and most weather, in a region closer to space than home. But one mystery remains. Why does the same sky glow green, red, blue, or purple at different times? Much of the familiar green aurora begins with oxygen atoms energized high in the upper atmosphere. An excited oxygen atom briefly holds extra energy, then releases a photon our eyes see as green. Countless green emissions line up along magnetic pathways, blending into the smooth curtains seen from below. Each tiny flash is separate, yet together they become bands, rays, and moving sheets of light. A microscopic energy change can help build a glow spreading across miles of dark northern horizon. All sky cameras record the aurora's motion, revealing changes too subtle or fast for casual viewers. Auroral color does not come from ordinary heat, but from atoms releasing energy in specific ways. To someone roadside, the sky feels alive, yet its movement follows hidden magnetic structure high above. Below the aurora, snow, ice, and bare branches borrow color from light made many miles overhead. Green may be the famous clue, but higher above it, a quieter red can sometimes appear. Above the green layer, thinner oxygen can glow red where the atmosphere is even more rarefied. In thinner upper air, excited oxygen can hold energy longer before nearby collisions interrupt the process. A red aurora may spread like a faint ceiling above brighter green curtains below it tonight. Colors can suggest altitude, but real auroras overlap, mix, and shift across a moving upper atmosphere. The sky is not divided into perfect stripes. It is uneven, layered, and constantly changing above us. Higher up, fewer collisions allow some excited atoms to release light before losing energy another way. A camera may reveal faint red structures that human eyes barely notice in a dark field. Spectral measurements help scientists identify which gases created the light reaching cameras on the cold ground. Oxygen explains much of the green and red, but another atmospheric ingredient now enters the story. The camera leaves oxygen's slow glow and moves toward nitrogen, where sharper colors often appear. Nitrogen molecules can add blue, purple, and reddish tones during more energetic auroral activity near the lower edge. When incoming particles strike nitrogen, vivid borders can appear around the lower edge's green curtains. Purple rays may rise like vertical brushstrokes above a frozen lake, marking stronger activity below the glow. A color scene across the sky begins as countless molecular emissions happening too quickly to follow. Researchers combine ground cameras, satellites, and atmospheric measurements to reconstruct where the light was born overhead. Aurora color is not decoration. It is encoded by gas type, altitude, and incoming particle energy. From the ground, people see beauty while molecules overhead respond one collision at a time above them. Even frost crystals can reflect colors created more than 60 miles above the quiet winter landscape. If gases explain the colors, what organizes the light into curtains, arcs, and rays across the sky? The investigation now follows the aurora's shape, not just the chemistry behind its color in the atmosphere. Particle pathways help organize the glow into long arcs, vertical rays, and shifting curtains overhead tonight. A single auroral arc can stretch across the sky like a luminous bridge over the horizon. From the ground it feels close, but the structure belongs to a planet-sized magnetic system above us. Auroras often gather in an oval around magnetic polar regions, not simply over the geographic pole. The oval is not fixed. It expands, contracts, and shifts as space weather conditions change above Earth. Bright patches can pulse and fade, hinting at waves and instabilities above the atmosphere during active nights. Standing beneath the lights, a person watches invisible forces briefly become visible in the air overhead. The visible curtain is the last step in a chain connecting the sun to Earth's upper air. But when that chain grows stronger, why can the lights move far beyond the Arctic Circle? The next chapter follows the glow outward, asking why auroras appear over some places, not others. Auroral light is not reflected sunlight. It is the upper atmosphere releasing energy after invisible particles arrive. This glow forms far above weather clouds, in a thin region most people never think about. Oxygen and nitrogen absorb incoming energy, then release photons as they settle back into quieter states high above Earth. In the visualization, one collision becomes visible, though real atoms remain far too small to see. From the ground, a viewer sees countless tiny emissions blending into one moving curtain of light. The aurora may look delicate, but it traces powerful electric and magnetic forces above Earth all night, green, red, and purple, toward different gases, heights, and energy conditions in the atmosphere. The same sky can change shape in seconds before the reason behind that motion becomes clear. The light returns to a real landscape, stretching over snow, trees, and a watching human face. Now the journey shifts from how auroral light is made to where that light gathers on Earth. If auroras come from the sun, why do they cluster around Earth's far northern and southern skies? Charged particles often follow magnetic field lines, guiding them toward the upper atmosphere near the poles. Earth's magnetic field shapes a global pathway, not a simple switch turned on above one place. An Alaska photographer may be standing still while a planetary scale system moves silently across the sky. The tripod, snow boots, and camera make the cosmic process feel close enough to touch for a moment. Auroras gather near the poles because magnetic geometry guides much of the incoming energy there first. The glowing arc shifts because the incoming energy and magnetic structure are changing together over the planet. The auroral oval marks where particle impacts are most likely to make the upper atmosphere glow, but the oval is not fixed, and its movement can reveal how intense the storm becomes. The next mystery is why that glowing ring sometimes expands far beyond its usual polar home. In northern landscapes, auroras feel local, yet they belong to a ring circling magnetic poles above Earth. From space, the lights form an oval zone, not a single beam over one frozen town. The field's shape channels particle motion toward high latitudes, where atmosphere and magnetism meet most directly. During stronger activity, parts of the northern United States can sit closer to the auroral oval. A quiet highway can become an observatory when space weather bends the night toward home, on snow and dark water, the aurora leaves faint reflections that make the sky feel lower. The visible glow sweeps across the landscape, while the real driver remains far above sight and sound. Aurora location depends less on ordinary geography than on how Earth connects magnetically to space overhead tonight. Where field lines meet the atmosphere, particle impacts concentrate, and the sky becomes more likely to glow. Once the oval appears, its widening becomes a clue about how much energy is arriving from space. Why does this ring sometimes grow wide enough for millions farther south to notice it after dark? Stronger solar wind and magnetic conditions can pour more energy into Earth's near space system than usual. The aurora behaves less like a lamp and more like a weather pattern driven from space. Forecasters watch these conditions because stronger storms can push the auroral zone far beyond the Arctic. Forecast maps show probability and possible extent, not guaranteed sightings, above every town on the map. For some Americans, a strong storm can bring the northern lights closer than a distant vacation. A faint southern aurora may look modest, yet it can reveal unusually strong space weather overhead. Cameras, tripods, and phones share the scene with a display driven by invisible charged particles from space. If space weather can move auroras, what else can it disturb along the way toward Earth? The story now prepares to connect glowing skies with the invisible technologies underneath them later in the journey. Sometimes auroras appear over familiar American landscapes, far from the Arctic wilderness people imagine at first. Visibility depends on storm strength, cloud cover, darkness, latitude, and how much city light interferes with the sky. When the oval expands, particle precipitation reaches atmospheric regions, farther from the magnetic poles than usual. Different colors may appear together because emissions happen at different heights and under different energy conditions. Color is a clue, but it cannot explain the whole aurora without altitude and gas context. Time-lapse can reveal folds, waves, and pulses the naked eye may completely miss in real time. Pulsing auroras suggest the magnetosphere feeding bursts of energy into the upper atmosphere tonight. Stored energy in Earth's magnetic tail can release suddenly, brightening auroras across the night side of Earth. Lights above a city raise a quieter question about the hidden systems working below them every night. Next, the video moves from where auroras appear to what stronger storms can mean for modern life. During stronger geomagnetic activity, the auroral oval can widen, bringing polar light closer to familiar northern horizons. Across quiet northern landscapes, the first sign may be a pale green edge above frozen trees. For a viewer outside at midnight, aurora often begins as a faint change in the northern darkness. The oval does not drift like a cloud. It expands as Earth's magnetic system becomes more disturbed. In a northern state, the spectacle might appear first as a low glow beyond the horizon. Forecast maps show probability and visibility lines, not promises that every backyard will see the lights. Aurora curtains seem to slide because shifting particle patterns are constantly redrawing light in the upper atmosphere. When auroras appear farther south, the light has not simply traveled across the sky like weather. A glow above a frozen lake can trace conditions that started far beyond Earth's protective shield. If the oval is widening tonight, something larger is changing inside the planet's magnetic environment. Auroras follow magnetic structure, which does not always match state borders, road maps, or simple geographic latitude. Two towns at similar latitude can sit differently on Earth's invisible magnetic map and see different skies. Over the Great Lakes, clear dark skies can become temporary windows into space weather above North America. Location matters, but darkness, clouds, timing, geomagnetic strength decide what people actually see from the ground. A bright city can erase faint aurora long before the magnetic system stops producing light above it. Space weather centers watch the sun, solar wind, and Earth's field before auroras fully develop. Measurements upstream of Earth help forecasters estimate what kind of solar wind is approaching the planet next. Sensitive cameras may catch faint green or red before human eyes recognize anything unusual overhead in darkness. The same magnetic system can paint skies over forests, lakes, coastlines, and empty winter roads across continents. But if the oval can grow, what force is feeding that expansion from space to night above Earth? As geomagnetic activity rises, the aurora can brighten, ripple, and occupy more of the northern sky. When solar wind couples more strongly with Earth's field, additional energy enters the magnetic system. The most beautiful display may also mark a stronger disturbance in the space surrounding Earth tonight. Scientists use activity scales to describe how unsettled Earth's magnetic environment has become during solar disturbances. Now the question shifts from where auroras appear to what powers their strongest nights above us. So when does an ordinary stream from the sun become storm, like around Earth's magnetic shield? From orbit, Earth looks small inside a flowing space environment that never truly sits still around it. Solar wind pressure can facing side of the magnetosphere, reshaping its outer boundary around Earth. At magnetic boundaries, field lines can interact, opening pathways for energy to enter near Earth space more efficiently. On the night side, stored disturbance can build before energy returns toward the upper atmosphere above Earth. Forecasters study incoming data, because effects near Earth may unfold after the earliest warning signs arrive. Solar wind speed matters, but it is only one clue inside a much larger forecast picture. The solar wind carries its own magnetic direction, and that direction can change the outcome dramatically. A fast stream alone does not guarantee the strongest geomagnetic response at Earth during every event. When the magnetic orientation is favorable, more solar energy can couple into Earth's protective shield. That extra energy may appear overhead as brighter, faster, more structured aurora across the polar sky. Aurora patterns reveal that the upper atmosphere responds unevenly, like a living electrical map above Earth. A small ripple above one town belongs to a magnetic system surrounding the entire planet tonight. Forecasting space weather means watching thresholds, probabilities, and changing conditions, not issuing simple yes or no answers today. The next question is how much disturbance the systems beneath that glowing sky can tolerate safely. Below the aurora, long power lines stretch across dark land like silent conductors, waiting beneath space weather. Changing magnetic fields can induce electrical currents in long conductors on the ground below our feet. During stronger geomagnetic events, unwanted currents can stress equipment built for ordinary power flow across regions. Grid operators use alerts and measurements to prepare, adjust, and reduce possible impacts before conditions worsen. Satellites face the changing environment directly, far above the protection of most air around Earth itself. Most people cannot feel space weather until instrument signals or essential systems begin to show it. High-latitude communication can be more exposed when storm conditions intensify above Earth's polar regions. Modern infrastructure is not separate from nature. It sits inside the larger Sun-Earth system every day. To understand the risk, we have to follow space weather into specific human technologies on Earth. The next clues are hidden in satellite signals, navigation screens, and power grids below the aurora. The aurora grows brighter, but that beauty is also a clue that Earth's magnetic environment is changing. From orbit, the glowing curtain becomes part of a larger storm, moving through the planet's magnetic field. Scientists measure geomagnetic storms across Earth, even when the aurora is visible only near northern horizons. Inside forecast rooms, researchers watch quiet screens that translate invisible space weather into readable public warnings. A small jump on one monitor, enormous magnetic motion, unfolding high above the atmosphere, like a city light seen from miles away. One aurora belongs to a much larger system. When strong solar wind arrives, Earth's magnetic shield can compress, stretch, and begin to store extra energy. The instruments do not show glowing curtains. They show fields, particles, pressure, and direction changing together. Satellites upstream of Earth can detect solar wind changes before the strongest effects reach the planet. The light above the snow is only the visible edge of a much wider space weather disturbance. On Earth's night side, the magnetic field stretches into a long tail pointing away from the sun. Inside that tail, magnetic lines can reconnect, releasing stored energy back toward the polar upper atmosphere. This glowing model is not the real field itself, but a simplified map of invisible motion. Once energy is released, charged particles can be accelerated along magnetic pathways toward the upper atmosphere. Particles too small to see can shape curtains of light spreading across hundreds of northern miles. The aurora may drift softly, yet the invisible forces behind it are moving with tremendous power. Researchers compare the sky's movement with satellite measurements, looking for the pattern behind the glow. Auroras do not appear as random stains. They often form organized rings around Earth's magnetic poles. During stronger storms, those rings can widen, carrying the lights farther from the distant polar regions. When aurora reaches farther south, it raises a bigger question about what else is changing below. Forecast teams read solar wind data carefully because the storm's impact depends on several conditions arriving together. Speed, density, and magnetic direction all help decide how strongly space weather disturbs Earth's shield. A southward magnetic direction can connect more efficiently with Earth's field, allowing more energy to enter. Fast solar wind alone does not guarantee a powerful storm. The magnetic alignment matters just as much. Forecast maps turn complex measurements into a practical estimate of where the aurora may appear tonight. A town can look completely calm, while instruments show the magnetic environment shifting far above it. Long power lines can act like conductors during strong geomagnetic disturbances, picking up unwanted electrical currents. Those induced currents are usually managed, but during major storms, they become a serious engineering concern. Grid operators monitor conditions so they can protect equipment before small disturbances become larger electrical problems. Electricity is only one connection. The same space weather also reaches satellites, aircraft, and radio systems. Modern technology does not sit outside nature. It operates inside Earth's constantly changing space environment. Satellites orbit above most weather, but they still move through a region shaped by solar activity. Signals from those satellites must cross the ionosphere before a receiver can turn them into location. During space weather events, the ionosphere can change, bending or delaying signals that pass through it. For most people, that invisible journey appears as a simple moving dot on a phone map. That ordinary blue dot depends on timing signals traveling through a sky that can become disturbed. During strong storms, navigation systems may face positioning errors, interruptions, or reduced reliability in exposed regions. Radio communication can also shift, because some signals depend on atmospheric layers, reflecting them back toward Earth. The aurora can look peaceful, while entire modern networks depend on conditions no one can see. So the next question is not only why the sky glows, but which machines are listening. Space weather reaches modern technology through the invisible upper environments. Those machines depend on every second. Navigation satellites send precise timing signals toward Earth, repeating a quiet measured rhythm from high orbit. GPS accuracy depends on that timing remaining clean as signals travel through the upper atmosphere. Overhead, a driver sees a route, not the chain of satellites, clocks, and charged particles behind it. The map feels local, yet its accuracy depends on signals crossing a restless layer of sky. Aviation, especially near high latitudes, watches space weather because routes and communications can become more vulnerable. During strong events, polar communication links and navigation support may face more difficult operating conditions overhead. Radio signals rely on atmospheric behavior, so changing ionospheric layers can alter where messages actually travel. Operators monitor these systems because space weather risk changes with storm strength, location, and technology design. Beyond the glowing sky, a quieter question remains: how many machines are connected to the sun? The aurora still glows above Earth, but below it, invisible signals are crossing the same disturbed space. Every GPS signal must pass through the upper atmosphere before it reaches a phone, dashboard, or aircraft. If that charged layer changes, the signal can arrive slightly late, and position estimates may drift. On a quiet highway, a tiny timing error can appear as a map that hesitates for seconds. The same storm painting the northern sky can also bend the path of navigation signals below. What looks local from the ground is part of a magnetic disturbance wrapped around the planet. GPS depends on clocks so precise that even small delays can matter to the final location. When charged particles disturb the ionosphere, satellite signals may slow, scatter, or shift before arriving at receivers. The danger is not always dramatic failure, but a quiet uncertainty building inside trusted measurements over time. And GPS is only the first machine listening through this restless layer above Earth every day. Above the aurora, satellites keep working in an environment that is not empty or still at all. Their metal surfaces, solar panels, and sensors face particles that ordinary machines on Earth never meet. During stronger storms, electrical charge can build on spacecraft surfaces or interfere with sensitive components inside. Most satellites do not fail spectacularly. Operators watch for subtle anomalies before they grow serious enough. A quiet row of numbers can tell engineers when a spacecraft is feeling the storm overhead. Strong geomagnetic activity can heat the upper atmosphere, making it expand and increase orbital drag slightly. Across many orbits, that drag can change how satellites move and how often they need correction. Inside control rooms, the response is not panic, but careful monitoring, adjustment, and planning ahead for changes. The machines most exposed to space weather are also some of the machines measuring it directly. But another system depends on the same charged, sky-long, distance radio communication through the ionosphere above. Over polar routes, aircraft can pass beneath auroras while flying through regions sensitive to space weather. A polar shortcut may save fuel, but it also crosses a place where radio signals can struggle. For crews and dispatchers, space weather becomes one more condition to track before, and during flight, high-frequency radio works by using the ionosphere almost like a changing mirror above Earth. During flight, when that mirror is disturbed. Signals that should bend back can weaken, scatter, or disappear unexpectedly. Aviation planners do not treat auroras as fear, but as information about the route ahead tonight. The more energy enters the upper atmosphere, the less reliable some radio paths may become temporarily. For a traveler, the glow is beautiful. For operators, it can be a useful warning sign. The risk is usually managed through forecasts, procedures, and backup systems, rather than emergency drama alone. From the sky, the story now descends to the long wires crossing the ground below cities. Power lines stretch quietly across the landscape, but they can still respond to magnetic change overhead. A disturbance surrounding the planet can reach the ground as currents moving through long conductors below. These geomagnetically induced currents are not lightning. They are slow electrical shifts driven by changing magnetic fields. During severe storms, those currents may stress transformers and force operators to manage the grid carefully. The vulnerable parts are often silent, heavy, and hidden behind fences, gauges, and control panels nearby. Preparation means watching space weather early, adjusting loads, and keeping crews aware before conditions peak seriously. A city may look normal while unseen systems track a storm arriving from the sun above. The reversal is strange. Even solid ground can answer an event that began in space far away. Aurora alone is not a crisis, but severe geomagnetic storms deserve serious attention from grid operators. That raises the practical question: how much warning can scientists give before the storm arrives here? A satellite, a radio signal, and a power line all share one environment above. They seem separate on Earth, yet each depends on conditions in near Earth space above us together. Standing under auroras, a person is also standing beneath navigation, communication, and electric systems still working. The lights are scenery to the eye, but diagnostic signals to those watching the planet carefully. Impacts depend on storm strength, timing, location, and the systems exposed, not aurora itself alone overhead. To become useful, space weather must be measured, interpreted, and turned into guidance for people on Earth. So the investigation leaves the machines below and turns back toward the sun for answers again. How do scientists see a storm coming before its particles have reached Earth at all yet? Sometimes the first warning is not a bright sky, but a subtle change on the sun. The next chapter follows those signals, from solar observation to forecasts that protect Earth systems below. How do scientists know the northern sky may glow before the first green arc appears tonight? Inside the forecast room, people compare quiet screens, looking for patterns that machines cannot judge alone. The story begins on the sun, where bright magnetic regions move across a restless surface constantly. A close solar image becomes evidence, showing dark spots, bright loops, and changing magnetic structure over time. Instruments turn sunlight into measurements, letting scientists compare today's sun with hours and days before. When activity strengthens there, Earth may feel the disturbance later, though the outcome is never automatic. Spacecraft keep watching when clouds, daylight, or distance would hide the sun from ground observers below. The warning travels across a gulf wider than any highway, yet instruments can still read it. The brightest solar image is not always the best clue. Sometimes the useful signal is quieter. From the sun's surface, the investigation moves outward into the invisible stream between worlds and planets. A small spacecraft waits upstream from Earth, sampling particles before they reach the magnetic shield ahead. Its instruments measure speed, density, temperature, and magnetic direction inside a flow no eye can see. The solar wind becomes understandable only when sensors translate invisible particles into numbers over time carefully. Those numbers can become early warnings when conditions suggest Earth's magnetic field may soon be disturbed. Against the vast solar wind, one spacecraft is tiny, but its measurements can guide an entire forecast. Even with good measurements, the question remains, how will Earth's magnetic shield actually respond next? Speed matters, but magnetic direction can decide whether solar energy slips more deeply into the system. When the signal points the wrong way, forecast maps may expand the expected aurora zone tonight. Between the sun's message and Earth's answer, a narrow window of uncertainty always remains. Raw measurements now move into models, where changing numbers become a forecast humans can actually use. Space weather forecasting is not casual watching, it is operational science following a moving target above Earth. A small shift on one chart can change where tonight's aurora might be visible from Earth. Models estimate where upper atmosphere gases may glow using current measurements and known magnetic behavior above Earth. Forecasters still weigh context because a living system rarely follows one simple line perfectly in space. For viewers, the planetary question becomes simple. Will the glow reach my horizon tonight or not? The auroral oval is not a fixed ring. It swells, shifts, and tightens with changing conditions. Why can a forecast change so quickly, even after the sun has already sent its stream? Like a storm forecast, an aurora forecast improves with data, but remains a probability for viewers. Even a strong prediction still needs dark skies, clear weather, and the right viewing direction overhead. The forecast leaves the control room and meets the ordinary landscape beneath the northern sky outside. Across Alaska or the Great Lakes, someone steps outside, checking a phone against the horizon carefully. The map offers a chance, not a promise, because the atmosphere and local weather still matter. Clouds, moonlight, and city glow can hide a weak aurora before it reaches the human eye. A bright forecast map may look certain, but the real test happens above one backyard tonight. Sometimes a camera sees the first faint color before a person can recognize it clearly unaided. Then the curtain strengthens and the forecast becomes a living green arc across the open sky. But a quiet horizon does not always mean the science failed. Conditions may have shifted suddenly. Visibility depends on solar activity, magnetic geometry, darkness, cloud cover, and the observer's latitude below. The same forecast guiding skywatchers also helps operators prepare satellites, radios, and electric systems below Earth. So the aurora prediction becomes more than travel advice, it becomes situational awareness from space weather. Each update narrows the unknown, but no forecast can erase the system's natural variability completely. A warning scale summarizes risk, while local effects still depend on timing, location, and infrastructure details. Probability is not confusion. It is the honest language of a changing solar environment above Earth. The sun does not send one perfect signal, but a stream that twists and evolves constantly. Forecasting works because scientists adapt, comparing each new measurement with what the model expected earlier today. From one room of monitors, the view expands to Earth moving through solar weather continuously overhead. When prediction, darkness, and magnetic conditions align, invisible physics becomes visible above the world below us. For the person watching, all that data becomes silence, cold air, and moving light overhead tonight. The final question is no longer only how auroras form, but what they reveal about Earth. This warning glow is beautiful, it's protected, and meaningful because Earth remains connected to space. A forecast screen can predict the glow, but the real answer waits outside under the northern sky. The roadside is silent, snow brightening slightly as the first green arc lifts above the trees. Standing beneath it, one person becomes the scale for a system that reaches all the way to the sun. The curtain moves slowly, turning the sky into evidence of energy, traveling through invisible magnetic paths. Even frost on a car hood catches the glow, like city glass reflecting a distant storm. That light begins when guided particles give energy to thin gases high above the ground at night. So the aurora is not only scenery, it is information written across the upper atmosphere in light. Earth's magnetic shield shapes where that information appears, drawing the glow into rings near the poles. The shield protects life below, yet it also proves Earth is still connected to space above us. Seen from the ground again, the same planetary system becomes a quiet arc over black spruce. Beneath the moving light, towns and roads sit inside an environment much larger than ordinary weather. Power lines crossing the snow remind us that modern systems also live under the same sky. That is why instruments keep watching, even when the aurora looks calm from the roadside tonight. Measurements turn invisible solar conditions into warnings. Forecasts and cautious decisions made before problems appear on Earth. When the solar wind changes, the auroral oval can answer with new shape, brightness, and reach. But the forecast is not a script that keeps part of its uncertainty alive. Satellites extend human sight beyond the ground, watching the sun, Earth system from above the atmosphere continuously. For the observer below, knowing the cause does not shrink the wonder, it only deepens it. The air we breathe becomes a canvas, glowing when particles arrive from far beyond Earth itself. Now the investigation returns to stillness, with the mechanism explained and the mystery widened above us. A single figure under the aurora shows how small human life is beneath this connection overhead. Understanding the light does not make it ordinary. It makes the silence above feel even larger. A single snow crystal can hold the same green light that circles the planet from orbit. From one reflected point, the story expands again to atmosphere, magnetic field, Earth, and distant sun. The final reversal is simple: Earth is protected, but it is never separate from its star. Auroras form when charged particles follow magnetic paths and make high atmospheric gases release visible light. That same space environment touches satellites, navigation, radio, and power systems people rarely notice directly below. The lesson is not fear, but humility about living beneath a star that never truly rests. What else crosses space silently? It finally becomes visible in the world around us here. When the sky glows again, we may see beauty, warning, and connection at the same time.